solutions from exercise 10.2 from the chapter Circles. So in the first question they've given that from a point Q, the length of the tangent to a circle is 24 centimeters, and the distance Q from the center is 25 centimeters. We need to find the radius of the circle. We know that any line drawn from the point of contact of the tangent to the circle is perpendicular from the radius. So that means that this equals 90 degrees. So that means this PQOP is a right angle triangle. And in order to find one of the unknown sides in a right angle triangle, we need to use the Pythagoras theorem. So here, this would be the hypotenuse. So 25 squared is equal to OP squared, which is the radius, plus 24 squared. So 25 squared is equal to 625. 625 minus 24 squared is 576, which is equal to OP squared. 625 minus 576 is equal to 49. So 49 is equal to OP squared. And OP is equal to root of 49, which is equal to 7. And they've given 4 options. And those options are 7, 15, 12, and 24.5. And out of which option A equals 7. So the answer is A. In the second question they've given that in figure, if TP and TQ are two tangents to a circle with center O, so that POQ is equal to 110 degrees, we need to find the angle PTQ. So since PT and PQ are two tangents, that means, and since O is the radius of the circle, or is the center of the circle, and we know that any line drawn from the point of contact to the radius is perpendicular, meaning these two angles are perpendicular, and this whole thing, POQT, this figure, is a quadrilateral, and we know all angles in a quadrilateral equate to 360 degrees, and we know three angles of this quadrilateral, and we need to find the angle T, PTQ. So we can say that 110 degrees plus 90 degrees plus 90 degrees is equal to 180 degrees, plus angle PTQ is equal to 360 degrees. So we know that 110 plus 180 is equal to 290 degrees, plus angle PTQ is equal to 360. Angle PTQ is equal to 360 minus 290, and angle PTQ is equal to 70 degrees. So the answer is equal to 70 degrees, and the correct option would be B, which is 70 degrees. In the third question, we're given that if tangents PA and PB from a point P to a circle with center O are inclined to each other at angle 80 degrees, we need to find POA. So they're asking us to find this angle. So we know that at the point of contact, any line drawn to the radius would be perpendicular. So these two angles would be 90 degrees. Since they're asking us to find POA, we can take in triangle POA, we know that angle P is equal to 40 degrees. Angle A is equal to 90 degrees. We're saying that angle APO is equal to 40 degrees because it is inclined at 80 degrees, and a line drawn from the radius to the point of inclination between two tangents is the angle bisector of the angle formed between two tangents. So that means 80 degrees divided by 2 is equal to 40, so these two angles will equal 40. So we know that angle P plus angle A plus angle O is equal to 180 degrees. We know 90 and 40, so 130 degrees plus angle O is equal to 180 degrees. So we can say that angle POA is equal to 180 degrees minus 130 degrees, and angle POA is equal to 50 degrees. And the option which satisfies our answer is A, which is equal to 50 degrees. In the fourth question, they're asking us to prove that the tangents drawn at the ends of a diameter of a circle are parallel. So we're going to take AB as the diameter of the circle and PQ to be two tangents. We know that the angle PAO is equal to 90 degrees because we know that a line drawn from the point of contact to the radius is perpendicular, so PAO is equal to 90 degrees. And then we can say that angle OBQ angle OBQ is equal to 90 degrees because of the same reason that a line drawn from the point of contact of a tangent to the radius is equal to 90 degrees. So we can say that angle 1 is equal to angle 2. And since angle 1 and angle 2 are alternate interior angles, and the diameter is the transversal line between two parallel lines, we can say that P is parallel to Q. In the fifth question, they're asking us to prove that a perpendicular at the point of contact to the tangent to a circle passes through the center. So in the given figure, AXB is the tangent to the circle with center O. Here, we can say that OX is the line perpendicular to the tangent AXB. So we can write OX is the line perpendicular to the tangent AXB at the point of contact X. So here we can say that angle OXB plus angle BXY is equal to 90 degrees and is equal to 90 degrees plus 90 degrees, which is equal to 180 degrees. That means we can say that OXY is collinear because the sum of angles OXB plus BXY is equal to 180 degrees. So we can say that OXY is collinear. So OX passes through the center. In question number 6, they've given that the length of a tangent from point A at a distance 5 centimeters from the center of the circle is 4 centimeters. Find the radius of the circle. So they've given the distance between AP is 4 centimeters, distance between A and radius is 5 centimeters. This would be the radius. We know that a line drawn from the point of contact of the tangent to the radius is perpendicular, so making AO the hypotenuse. So using the Pythagoras theorem, we can find the unknown value PO of the right angle triangle PAO. So in triangle PAO, we can say that AO squared is equal to AP squared plus PO squared. AO squared 25 minus AP squared, which is 16, is equal to PO squared. 25 minus 16 is equal to 9 is equal to PO squared. PO is equal to the whole root of 9. So PO is equal to 3. In the 7th question, they've given that two concentric circles are of radius 5 centimeters and 3 centimeters. We need to find the length of the chord of the larger circle which touches the smaller circle. So they're asking us to find the distance of PQ. So we know that the radius of the smaller circle is OR, which is equal to 3. The radius of the larger circle is PO, which is equal to 5. So this would make 90 degrees because OR is perpendicular because PQ is a tangent to the smaller circle, and any line drawn from the point of contact to the radius of the circle is perpendicular. And since this is a right angle triangle, we can say that in triangle POR, 5 squared plus PR squared. 5 squared is equal to PR squared plus 3 squared. So 25 minus 9 is equal to PR squared. 16 is equal to PR squared. PR is equal to 4. and RQ is equal to PR, and PR plus RQ is equal to PQ, which is what they're asking us to find. So PR plus RQ is 4 plus 4 is equal to PQ. So PQ is equal to 8. In the 8th question, they've given that a quadrilateral ABCD is drawn to circumscribe a circle. We need to prove that AB plus CD is equal to AD plus BC. So since we know that the quadrilateral DABC circumscribes the circle, and here we will notice that DS and DR are two tangents drawn from the same point, and we know that two tangents drawn from the same point are equal, so we can say that DS is equal to DR. Similarly, CR is equal to CQ. And BQ is equal to BP, and AP is equal to AS. So now they're asking us to prove that AB plus CD, they're asking us to prove that AB plus CD is equal to AD plus BC. So now let's name this as 1, this is 2, 3, and 4. So if we add 1, 2, 3, and 4, we will get AP plus BP plus CR plus DR is equal to AS plus BQ plus CQ plus DS. So AP plus BP is equal to AB. CR plus DR is equal to DC, which is equal to AS plus DS, which is equal to DA, and BQ plus CQ, which is equal to CB. So this is what they're asking us to prove. AB plus CD is equal to AD plus BC. In the 9th question, they've given that in figure XY and X dash and Y dash are two parallel tangents to a circle. X with center O and another tangent AB with point of contact C, intersecting XY at A and X dash Y dash at B. We need to prove that angle AOB is equal to 90 degrees. So first, let's take the two triangles PAO and AOC. So in triangle PAO and triangle AOC, we can say that PA is equal to AC because there are two tangents drawn from the same point. Next, we can say that OP is equal to OC because they're both the radius of the circle. And we can say that OA is equal to OA because they're common. So using the SSS criterion, we can say that triangle PAO is congruent to triangle AOC. So by CPCT, we can say that angle POA is equal to angle AOC. Next, in triangle COB and triangle BOQ, we can say that OC is equal to OQ because they're both the radius of the circle. OB is equal to OB because they're both common. And CQB is equal to BC because they're tangents drawn from the same point. So they're asking us to prove that angle AOB is equal to 90 degrees. And we know that POQ is a straight line, so all these angles will add up to 180 degrees. So we can say that angle POA plus angle AOC plus angle COB plus angle BOQ is equal to 180 degrees. And we know that AOB is equal to angle AOC plus angle COB. And we know that APOA is equal to AOC, and COB, angle COB, is equal to angle BOQ, because they are using the corresponding parts of a using the CPCT criterion. We can say that COB is equal to BOQ because both of these triangles, COB and BOQ, are congruent due to the SSS criterion. So we can write, since we know that POA is equal to AOC, we can write 2 AOC plus 2 COB, because BOQ is equal to COB, is equal to 180 degrees. If we take 2 commonly outside, we will get 2 angle AOC plus COB is equal to 180 degrees. Angle AOC plus angle COB is equal to 90 degrees. So angle AOC plus angle COB is equal to AOB, so we can write angle AOB is equal to 90 degrees, hence proved. In the 10th question, they're asking us to prove that the angle between two tangents drawn from an external point to a circle is supplementary to the angle subtended by the line segment joining the points of contact at the center. So we know that angle PAO is equal to 90 degrees and angle PBO is equal to 90 degrees. And we know that OAP is equal to OBP, which is equal to 90 degrees. So in quadrilateral APBO, we can say that angle PAO plus angle PBO plus angle AOB plus angle APB is equal to 360 degrees. And we know that PAO and PBO both equal to 90 degrees, so we can write angle PAO plus 180 degrees is plus angle APB is equal to 360 degrees. So angle PAO plus angle APB is equal to 180 degrees. And they're asking us to prove that the angle between the two tangents drawn from the external point is supplementary to the angle subtended at the center of the circle. So hence proved. In the 11th question, they're asking us to prove that the parallelogram circumscribing a circle is a rhombus. So we have a parallelogram ABCD which circumscribes a circle with center O, P, Q, R, and S are the points of contact of the sides AB, BC, CD, and DA respectively. So we can say that in triangle ORC and triangle OSA, angle ORC is equal to angle OSA because they're both equal to 90 degrees. We can say that OC is equal to OA because O is the midpoint of AC. Similarly, OR is equal to OS because they're the radius of the circle. So we can say that triangle ORC is congruent to triangle OSA by the RHS criteria, congruency rule. And we can say that RC is equal to AS by CPCT, and DR is equal to DS because they're tangents from a point. So when we're going to name this as 1 and this as 2, and when we add both of these two equations, we will get RC plus DR is equal to AS plus DS. So RC plus DR is equal to DC, and AS plus DS is equal to AD. So we have proved that AB is equal to DC and AD is equal to BC. And since ABCD is a parallelogram, we can say that ABCD is a rhombus. In question number 12, they've given that a triangle ABC is drawn to circumscribe a circle of radius 4 centimeters, such that the segments BD and DC, into which BC is divided by the point of contact D, are lengths 8 centimeters and 6 centimeters respectively. We need to find the sides AB and AC. So we know that we can name this triangle as A, B, C. This point will be F and E, and this would be D. So we know that BD is equal to 8 centimeters, DC is equal to 6 centimeters, and we can say that BE is equal to BD, which is equal to 8 centimeters, and CD is equal to CF, which is equal to 6 centimeters. And we're going to take AE is equal to AF, which is equal to X centimeters. And in triangle ABC, A is equal to 6 plus 8, which is equal to 14 centimeters. So B is equal to X plus 6 centimeters, and C is equal to X plus 8 centimeters. So this part is going to be A, this part is going to be B, and this is going to be C. So side C is equal to X plus 8 centimeters, side A is equal to 14 centimeters, and side B is equal to 6 plus X centimeters. So using the Heron's formula, we know that the semi-perimeter is equal to A plus B plus C by 2. So the semi-perimeter of the whole triangle would be 14 plus X plus 6 plus X plus 8 by 2, which is equal to 2X plus 28 by 2, which is equal to X plus 14 centimeters. So in order to figure out the value of X, we're going to find the area of the whole triangle. And the area of the whole triangle will be equal to the area of this triangle, and this triangle. So the area of ABC would be equal to the area of AOC plus area of COB plus area of AOB. So we're going to find the areas of those three triangles separately. So using the Heron's formula, we can say that area of ABC is equal to S times S minus A times S minus B times S minus C. So substituting the values we found, we would get X plus 14 times X times 8 times 6, which is equal to root of 48X times X plus 14 centimeters. So we can say area of triangle ABC is equal to area of OBC plus area of OCA plus area of OAB. So area of ABC would be half into base, which is 4, times height, which is A, plus half into the base is A and the radius is 4, and half into the radius times base, which is B, plus half into 4, which is the radius, and base is C. So we will get, when we simplify this, we will get 2A plus 2B plus 2C, which is equal to 2 times A plus B plus C. And we know that the values of A plus B plus C is equal to X plus 14. So that would basically be 2 times twice of X plus 14. So when we add all of the areas of the three triangles, we will get 4 times X plus 14. And we know that the sum of all three areas of the triangles would be equal to the area of the whole triangle, which we found here, which is root of 48 times X plus 14. If we square on both sides, we will be able to cancel the root. So we will get 48 times X plus 14 is equal to 16 times X plus 14 the whole squared, and when we simplify this, we will get 3x times x plus 14 is equal to x plus 14 the whole squared. This is because we bring 16 over to the right hand side, it becomes division, 48. So now we'll be able to cancel x plus 14 squared and x plus 14. So we will have 3x is equal to x plus 14. So we can say 2x is equal to 14 and the value of x is equal to 7. So we can say AB is equal to x plus 8. So AB is equal to 7 plus 8, which is equal to 15. AC is equal to x plus 6, so 7 plus 6 is equal to 13. And now we have found the two sides of the triangle. In the 13th question, they're asking us to prove that the opposite sides of a quadrilateral circumscribing a circle subtend supplementary angles at the circle, at the center of the circle. So from the figure, we will observe that OA bisects angle SOP. So angle OA bisects angle SOP. So that means angle A is equal to angle B. Similarly, we can say that angle C is equal to angle D, angle E is equal to angle F, and angle G is equal to angle H. So when we add all of these equations, which we'll name 1, 2, 3, and 4, when we add all of them, we will get A 2 times angle A plus angle H plus angle E plus angle D is equal to 360 degrees. The reason it is 2 times angle A plus angle H plus angle E plus angle D is because when we add all of the equations, we will get A plus C plus E plus G, which is equal to B plus D plus F plus H, and since A is equal to B, we're going to write that as 2A plus 2H plus 2E plus 2D, and when we take 2 outside, we will get 2 times A plus H plus E plus D, which is equal to 180 degrees. So here, when we bring 2 over to this side, we will get A plus H plus E plus D is equal to 180 degrees. And we can write A plus H plus E plus D is equal to 180 degrees, and we know that A plus angle H is equal to angle AOB plus angle E plus angle D is equal to angle DOC, which is equal to 180 degrees. Similarly, we can say that angle AOD plus angle BOC is equal to 180 degrees. Hence proved. Hence we have proved that the opposite sides of a quadrilateral ABCD subtend supplementary angles at the center of the circle.